This is the Computer Programming University, and today we are going to be listening to a Python no, we're going to be listening to not an Python expert, a Python expert talking about coding in Python in terms of from a perspective of speed, focused on speed, memory, usage, and things like that, like how to make your code faster. So we're going to look at some advanced concepts and techniques to consider when you're trying to optimize your code. Now, I've been working in finance for almost 2 decades now, and I can tell you, when we look at software design, speed is of essence, especially in high-speed trading, where you're looking at things like microsecond, benchmarks. Like that's what they're looking at. They want response times in the microseconds. So obviously, speed is of utmost essence. So these are definitely things that we focus on in the industry. But regardless, let's get right into it and let's learn about how to make our code faster and more efficient and ultimately better. And additionally, I am going to be covering some design concepts in the future. So we're going to be going through the full SDLC process in terms of how you develop your code. It's one thing, hey, I know Python, right? You know the syntax, you know how to do your loops, you know how to do classes, you know all that good stuff. But can you do it well? Like, do you understand the principles of software design, right? You want to be a software engineer or just a programmer? Like, what are you looking to do? So anyway, we'll be going through concepts of software design in future episodes. So if you're new, definitely subscribe and smash that bell. But anyway, let's get right into the presentation. Let's begin. Oh yeah.
Catalog of high quality.
Let's think about this in a different way. Let's think about some function that takes a lot of time to do something, right? Maybe a function that goes off and performs network requests, and it needs to load data from a database. What would that function look like? Well, it might have the resulting rows, and it might say, while db.read rows.append something. Now, this will be a little bit tricky for us to actually demo, so we'll do a couple of simplifications just to make this code look, kind of mimic what long-running computational code looks like, but without actually having to use any fancy libraries. So let's say what we have instead is we have some code, and it just sleeps for a half a second every time it provides a return value. And the return value will just be a number from 0 to 9. Let me ask you a question. We'll call this we'll just call this compute. Whoops. When I call compute, how long does it take to run? Five seconds. What if I only care about the first return value? What if I only care about the first value? How long does it take to run? What if I care about the first 3 values? How long does it take to run? How much memory, in terms of, if we just make very simple assumptions, how much memory does compute require? 10 units of memory, 10 integers in a list, right? What if I only care about the first value? How much memory does it use? Same, right? What if I care about all the elements? How much memory does it use? Same. This is what we often mean by eager. The idea that this function, irrespective of what you actually care about in this computation, always takes the exact same amount of memory and the exact same amount of time. It eagerly gives you the entire result, and you're sitting there waiting for the entire result. So you can see it gives me the entire result all at once. This is undesirable, because if this happens to be not 0.5 seconds, but 5 seconds, then I have to wait 50 seconds before I can even start processing the very first entry. And so I'm sitting there blocked, waiting for 50 seconds, when maybe I could process these one by one. Also, if this is not 10 entries, but 1,000,000 entries, maybe I only want to look at them one by one. I don't need to have the whole history of all the entries. I'm now spending gigabytes of memory just so you can eagerly give me the entire result set, when I only care to look at them one by one, and the moment I look at one of them, I could throw it away. So you can see this is both wasteful from the perspective of the time that it takes, and wasteful from the perspective of the amount of memory it takes. Let's think if there's a better way to do this. And let's think about this in terms of our object model. Let me rewrite compute as a class. So it doesn't take any arguments, and I'll just dump this stuff underneath. Nothing very.
Have a second, take a look through the Node.js docs.
A class. So it doesn't take any arguments, and I'll just dump this stuff underneath. Nothing very interesting here. But more or less does the exact same thing, really no difference between the two versions. So I haven't gained anything here. I haven't gained anything by feeding into my object model. That said, I've kind of seen this pattern before. I've seen this pattern of I only want one element at a time, and I'm going to get each element, and as I get each element, I'll process it and maybe throw it away. It's a basic looping construct. In fact, I see it even here in this looping construct here. I don't get the entire list at once. I only get each one individual element of the list. And one thing that we might know is that in Python, we see top-level syntax or top-level functions has some corresponding underscore methods that implement it. If I told you that there's a pattern, if I told you that there's some syntax for x and xs, and I told you that this syntax actually looks like this, more or less under the covers, you could probably guess what the underscore functions we have to implement would be. They'd correspond to these two top-level functions here and here. They'd be iter, and they'd be next. So what that means is we can take a class in Python, we can add an iter and a next method, and suddenly that class can be iterated over. Well, in the process of that iteration, what could we do? Well, anything arbitrarily, including perform a long computation. So what we could do, and what the iter method actually needs to return, you'll find out when you read the documentation. It's not that important. We'll just return self. The next method just gives you each next method that you iterate over. Well, instead of putting the computation in this eager call method, what if I did this? What if I have the iter method say the last number I looked at was 0, and I do this. I say self.last plus equals 1. If self.last is greater than, and we'll limit this loop back to 10, just to keep our lives sane. It's greater than 10. Raise stop iteration. Otherwise, we sleep for 0.5 seconds, and we return self.last. And we'll actually do, this will be slightly different, so we'll do it like this. Here. So there, this will give us the same thing. So now, slightly different order, but you can see now our next method computes what was the last value we looked at, captures it, it increments the last value we looked at. If there's too many, it raises a stop iteration. We won't worry about what that means just yet. It'll sleep corresponding to our long-running computation, and it'll return the value. Now notice something different between this compute method and this next method. This compute method returned a list of all the values. This next method returned a single value. And the way that you'd use it is as follows. You just print it out. You loop over and print it out. And we'll actually see that here in practice. You can see it's computing each value one at a time. And in this loop here, you can do something you want with it, like print it out. It still takes 50 seconds in total to print out the whole thing. But you only pay for, or it still takes 5 seconds in total to print out the whole thing, but you only have to pay for 1 unit of computation before you can start using that value. And it no longer requires 10 units of memory because there's no storage anymore. Notice, here there's no storage, and here there's no list, there's no storage. Well, this really looks ugly, and this is really hard to read. Just like this looks really ugly, and this is really hard to read, and there's a much simpler way to write it, a much simpler formal expression for how to write functions. There's a much simpler way to write a function that operates in this fashion. And that's what the generator syntax is. The generator syntax is merely something that looks like this. And all this means is this thing here, compute, is something that can be iterated over. Each time you iterate over it, this is the value that it will yield. The stop iteration naturally happens because if you try and iterate over this too many times, there'll be nothing left to yield because you'll have fallen off the end of this block here. Its state is maintained internally. It's just a function that kind of doesn't really return eagerly. You'd never want to write this formulation. This is just such a pain in the butt. You'd instead want to take the original function formulation and write it in its generator formulation. When you look at the function formulation and the generator formulation, and you squint your eyes, you can see all the same pieces in the same places. Except in one of them, you have storage, and you have eager computation of the entire result set. And in the other one, you have no storage, and you're simply returning values as you see them. This is the core concept behind a generator, and the core mental model behind a generator. That instead of eagerly computing values, you give them to the user as they ask for them. But there is another similarly important and critical core concept to how generators work, beyond just this. And that's what I want to show you leading up into our last example. We have all seen APIs that look like this. Run this first. We've all seen APIs that look like this, which have methods that indicate the order in which you have to run functions. If you don't run this first, everything blows up. If you don't run this last, everything blows up. And in the documentation, they tell you, please run this method, then this method, then this method, because if you do it in any other order, all hell breaks loose. Unfortunately, this API is kind of lying to you, because nothing stops you from being a dunderhead, so I don't like the word dunder, and doing this. Nothing physically stops you from putting these in the wrong order, other than that you fail to read the documentation, and you'll see it break. Well, one interesting thing about the generator formulation is that if you look at the generator formulation, you can see it performs some computation, then not only does it yield the result back, but it also yields control back to the caller. You can see here in this formulation, let's lowercase this, I perform one computation, one long-running computation modeled by this sleep. And then I give the value back to the user to do something with, and then they ask for the next computation, give it back to the user to do something with. So I'm kind of interleaving the user code and the library code. In the eager formulation, the library code ran to completion, gave the entire result set back to the user, then the user did whatever they want with it. In the generator formulation, I have a little bit of library code run, then a little bit of user code run, then a little bit of library code run, then a little bit of user code run. And I interleave them. This is the actual core conceptualization behind what the generators are built upon, the idea of coroutines. Subroutines we can think of as any piece of executable code that runs from some starting point to some ending point to completion. They have one single entryway, and they have one single entry point, and they have one single exit point, and that's it. They run, they're done. If you look at how user code and library code interact, if the subroutine is in library code, it runs to completion, and then the user code has to pick up. For the generator, or the coroutine, you enter the generator, and as you ask for values, the generator runs. But you can have this nice interleaving, where some user code runs, asks the generator for a value, the generator runs its code, yields back to the user code does whatever it wants, goes back to the generator, asks for another value, and so on. So you have this interleaving of the two pieces of your code, the user code and the library code. Here in this API, what we'd actually have is, similarly, when we use this API, we'd ideally want to have some interleaving. Because if we could run all three of these methods all at the same time, the API would never have provided us three methods. If we didn't have to have some code between these three calls, they would never be provided as different calls. If they could all be done at once, we would just have one method here called doIt that just calls first, second, and last, and make sure that we can't screw this up. So the reason that the API gives us these three pieces split into three parts is because they specifically intend us to interleave code. They just want to make sure we interleave code in a fixed sequencing, in a fixed order. Well, let's think about this. If I wrote this as a generator, we could do that interleaving while maintaining the sequencing. And this, I would say, is maybe even a more critical mental model for generators than this eager versus lazy divide. The idea that generators are a mechanism by which you can create code that can interleave with other code and also enforce sequencing. Notice here that what happens when this generator runs is it'll run up to this point, yield no value, but it'll yield control back to the caller. Then the caller can resume, and the caller can resume. In this particular formulation, first, second, and last will always run in that order. You can't guarantee that last will run, but you never can guarantee that someone could pull the plug before that runs. But here, if the API were provided in this fashion, you could guarantee that the last method was never called before the first or the second method. The generator forces that sequencing on you. And it forces that sequencing on you because the generator is ultimately a coroutine that allows you this interleaving between two types of code, user code and library code. Let's remember that, and we'll go into the final of the examples we want to look at, the context manager. Context managers are a very, very simple metaphor, and a common metaphor you see all over the place. If you're a C++ user, you've seen this metaphor before. You probably called it resource allocation is initialization, or something like that. If you're a Java programmer, you've seen this metaphor before, but I don't know what you call it in Java. I don't know if Java has a real name or concept for this. It's the idea that there's always some desire to do some setup and teardown, and you want to combine them. If you're a Python programmer, and you've done even very introductory stuff with Python, you've seen a context manager before. And it looks something like this. It's the most basic context manager that you've seen before. You open some file. And the reason you use a context manager here is that there's some corresponding setup and teardown. If you open the file, you got to close the file. This is especially true on Windows because on Linux, file locks are a little bit less aggressive. On Windows, if you don't close the file, you might not be able to delete it later. This is especially true if perhaps this file is backed by some storage where it's not necessarily automatically flushed, if there's some I/O buffering. Because definitely, if you open the file and you write to it, you want to make sure those are flushed to disk in case the program terminates at some point with unflushed I/O buffers. You might lose things that you intended to be written to disk. But fundamentally, there is this metaphor here, this idea that we have some setup action and some teardown action, some initial action and some final action, and we want to match them together. Let me show you an example of that. It goes beyond files, but it can go even into things like SQLite databases. So in SQLite, we have these file-backed databases. The connect method is actually a context manager itself. So here, I connected some database. I have some cursor on that database. And let me just do this. And I could do some statement. So I could do something like create table points, x int, y int. I have some statement to execute a table, maybe insert some things into this table. X, Y, values 1, 1. There we go. And then I have some statement where I could select from this. There we go. And then we could commit this. So here we have just very simple use of a context manager, wrapping some database operations. And what is it? It's not cur.commit. We don't need that, actually. And what we'll do is we also want to make sure that we drop our table when we're done. There we go. And so you can see the code ran. I'll do 2 selects just so you can see everything. And you can see our code ran. Now you can see that the idea of there being some setup and teardown action is pretty clear with the opening and closing of the database, right? Obviously, if we open the database and we write to it, we want to close it. But there's another setup and teardown action that you might not see here. See if you can spot it. If we assume that we did something and we want to have some corresponding action to undo it, what's the pair that you see here?
The table?
Yeah, I create a table and I drop a table. Now, naturally, if we were to really properly do this, we'd probably do it in a transaction, and a transaction would give us the right semantics. But let's assume that for SQLite, we might not have transactional support, so we have to be in charge of that pairing, that create and that drop. And naturally, it's a very natural pairing. You create something, you drop it. You want to make sure that both of them get done, irrespective of some error pops up in the middle. So how do we actually write our own context manager? And you'll see that this will bring together everything we've looked at so far. As I told you, it turns out, fundamentally in Python, there is always some top-level syntax or some function and some underscore methods that implement it. If I told you let's write it like this, ttx as x. If I told you that behind the scenes, this actually looked like the following. X equals ctx, enter. Try, finally. If I told you that, and I don't know what the argument, there's some arguments that get passed there, I don't care what they are. But if I told you that's what it looks like, you even know exactly what the underscore methods are. They're right in front of your face, right? Enter and exit. So that's how we write a context manager. We implement enter and exit. Now here you're going to see me really fumble.
This is the Computer Programming University, and if you enjoyed this episode, and if you can actually hear me over the music, go ahead and click on the like button, subscribe if you haven't subscribed already, and smash that bell. You know you want to. Thanks for watching, thanks for the likes, thanks for the subscriptions, and until the next episode, stay positive and stay on your grind. Also, I just want to let you guys know I have started a Discord. You definitely want to join a Discord community. We are working on some community projects. Right now, the major project that we're working on is building our own trading platform, which is going to be interesting for sure. I've been working in finance for almost 2 decades, and I've been intimately involved in the development process of some of the world's leading trading applications. So I'm gonna utilize some of that expertise and experience and bring that to the project. And right now I have a team of really cool developers that are working together on building that, and there's some other projects as well that we're working on. and it's really awesome. You know, it's really cool to go beyond the boot camps and school and do your own projects and things like that. But it's even better when you do real projects. Now, there's real projects in terms of from a job, you know, someone actually paid you to do. And there's real projects in terms of projects that you do that you're not getting paid for, but you try to achieve the same standards as if you were. Right? So you take on that same level of seriousness and that same level of sort of business philosophy on the project, but it's your own project. It's, you know, let's come together and let's build something really cool, and let's try to treat it as if it's an actual product. So let's have the same standards as a commercial product would, right? Performance, right? Stability, right? And so on and so forth. Like, just imagine if you were being hired to build something, what sort of standards would you be required to achieve, right? And we adopt those same standards within our own projects. So if you're interested in stuff like that, I definitely recommend you join the Discord and join us. Open invitation. This is the Computer Programming University, where learning is always fun, as it should be. Thanks for watching. Have an awesome day. And until next time, salut, adios, and ciao. That's entirely enough of that, and perhaps, just perhaps, you should get back to work. Yeah.